Okay, this is 7.4 part 2. And the next question is, what do covalence... So let me just do this first. Question, what do covalent solids look like? Okay, so in the last notes we discussed ionic solids, and it was repeating ions over and over again, ionic solids. Okay, so what do covalent solids look like? Answer. They can also form a crystal lattice. They also form a crystal lattice. And we call that crystal lattice a network covalent solid. And what a network covalent solid is, so number 2, network covalent solids. Individual atoms usually silicon or carbon bonded to each other covalently over and over again. Now let's think about this. Why is it normally silicon or carbon? Well, the answer is because they're the ones that have the most bonding sites. Silicon and carbon. Okay? So let's look at an example. This would be carbon bonded to itself over and over again. Okay? And this is what diamond would look like if you could zoom in. These are just, let's examine what this is. Let me just do this. This is one carbon atom bonded to another, bonded to another. So this is all just carbon bonded over and over and over again. Okay, the reason why carbon can behave this way is because it's got 4 bonding sites on it. Could you do this with oxygen? Could you try to make a crystal like this with oxygen? It would be very difficult. It'd be very difficult to do that because oxygen only has 2 bonding sites. But because carbon has 4, it can bond to itself repeatedly over and over. And when you get this carbon covalently bonded, you can form a crystal. You can form a crystal, or if it bonds in a different way like this forms graphite. So you can see the graphite kind of forms a layer, whereas diamond forms a crystal like this. They're both actually crystalline technically, even though we don't think of graphite as a crystal. If we were to zoom in, we could see a crystalline structure like this, okay, a lattice structure of repeated carbons bonded over and over again. And we call these network covalent solids. Network covalent solids. The other atoms that can do this are silicon. Silicon also has, I believe, 4 bonding sites, if I'm not mistaken, since it is in the carbon group, although it might behave a little bit differently, but that's neither here nor there. So if you take silicon and you bond it together with an oxygen, silicon dioxide, bonded over and over again, okay, to itself, then you get to form what's called quartz. And this is what it would actually, this is actual quartz, and this is a network covalent solid. Okay, this is what one looks like in real life. And you can see it is in fact a crystal. That's what it is. It's a crystal, and it's just a covalent molecule that's bonded to itself over and over and over again. So that's what these things look like. So what are the characteristics? Characteristics. got high melting points. Oh, it says 1600 to 3500 C. They're insulators, which means they're poor conductors. Poor conductors. And they are hard and or brittle. Okay, so that describes ionic and covalent solids. Then what about these guys right here? Where do we see these? Well, we see the IMFs in all other molecular solids. So here's what and what does that mean? So let's just ask this question. What do all other molecular solids look like? That's covalent. Answer. Covalent molecules we can think of it as of them being like clumped together. Using clumped together by IMFs. Okay, so let's think about what that might look like. Okay, here we go. They're clumped together. These are individual molecules, right? And they're covalent. They're all non-metals, and they're held together as little units, independent units, but they just kind of interact with each other in this sort of clumped together fashion. And all the biological molecules do this. And also you can think about like sugars and things like that. Sugars, waxes, if you look at like paraffin wax, candle wax, things of that nature. Okay, those are all covalent solids that are held together by IMFs. So examples include sugar. In this case we'll say C12H22O11. Biological molecules. Solid H2O, etc. Anything that's covalent that doesn't bond to itself, mostly carbon and silicon compounds that don't bond to itself over and over, they interact in solid form through IMFs. I'll try to go in the back and find some right now. Okay, this is dextrose, which is a sugar, and well, it's kind of tricky to see. You can see it definitely doesn't have that same sort of structural crystal that you find with quartz. The quartz or diamond that I just showed you. I showed you quartz. Okay, so while this would look crystalline under a microscope, and it is to a certain extent, it doesn't have those same sort of crystal characteristics. It's got a very low melting point. If I were to heat it up, it would melt, and it's very brittle. And this is, again, this is a sugar, and it's a covalent compound that is held together through IMFs rather than through bonds. Okay, and the IMFs that hold it together are going to be dipole-dipole or London dispersion. It does not have hydrogen bonds. So the characteristics are we can say less hard. That's not a very scientific term, but less hard and brittle. Low melting point. If you've ever heated up sugar, you know it melts and caramelizes very quickly. That's going to be less than 200 degrees Celsius. Okay, so now on the test, you're going to be given a set of characteristics and asked to classify the substance based on these characteristics. I'm going to go ahead and put that here, see if you can read it. Okay, on the test, you're going to be given a set of characteristics, and you will be asked to classify the substance based on these characteristics. So you'll be given like a little drawing of a crystal or clumps of molecules interacting with one another, or perhaps even asked to draw a Lewis structure, and then you're going to be asked which one of these characteristics, which one of these characteristics, or which group rather, the solid falls into based on the characteristics. Okay, and then the last question is, did you answer the tie-dye question? What forces do you think were at play between the two shirts? So we had two shirts. One was brightly colored, the other one was less brightly colored. And what forces do you think were responsible for that difference in color? And we'll discuss that a little bit in class as well.